which your central angle is created by an initial side of the coordinate grid, which is the right side of your x-axis, to this terminal side. The terminal side is important. All angles, however, will start at this initial side, which is at 0 degrees or 0 radians. We are going to find both positive angles and negative angles. So angles are no longer just positive. So positive angles are found moving clockwise. So if I take this and I move clockwise this direction, that's going to be a positive angle. Oh, I'm sorry, I meant counterclockwise. Excuse me. So as I'm going in this direction, we are going against the clock, counterclockwise. So that would give us a positive angle. If I started here, and again, remember I'm starting in this direction, if I go clockwise, which would be down here, that's now going to give me a negative degree angle. And so we're going to work with both positive and both negative today. And this side right here never changes. It's the terminal side that will always change. So let's look at what's called coterminal angles. Coterminal angles just mean that they're angles that share the same terminating side. And they all start at the same initial and they all end at the same side. So you're thinking, well, if they all start at the same initial and they end at the same terminal side, well, would that just be one angle measure? Couldn't I go from here to here to here? Couldn't I make a whole nother revolution? If this angle here is, let's say 60 degrees, this original angle, and I want a whole nother revolution, what's 60 degrees plus 360 degrees? 420 degrees. So a coterminal angle to 60 degrees would be 420 degrees, and they both share the same terminal side, and they share the same initial side. One angle is just going around more than the other angle. And I could do that over and over and over again. I could have an infinite number of angles that have a terminal side the same as a 60-degree angle. I would just keep adding 360 degrees over and over and over again. Same thing could be said if I wanted a negative angle. You gentlemen have notes on your desks.
Notes.
Thank you, thank you. So the same thing can be said of a negative angle. So again, if this is 60 degrees, so there's this terminal side, but I want a negative angle that has that same terminal side, I would still start from my initial side, but I'm going to go in the negative direction. So I'm going to go from here all the way to here. That is not a full revolution. If this is 60 degrees here, what would this be here? The whole thing is 360. It would be negative 330, wouldn't it? Because it would be 330 degrees, but I went in the negative direction, so it has to be negative 330. I'm going to show you how to find that mathematically. So let's look at example 1. So not only do you have to find, but you also have to draw exactly what I was just drawing there. So we're going to find and draw both a positive and a negative angle that are coterminal to given angles. And we're going to also look at radian measure as well. You have to get used to counting in radian measures. So let's just start with degrees. So draw a small coordinate grid here. I'm going to start with my angle of degree of 30 degrees, and I'm not going to be picky that you didn't draw a 30-degree angle. All I care about is that you draw the terminal side in the quadrant that it belongs. And so from here to here is my 30 degrees. I need a positive and a negative angle that terminates at that red side. So a positive angle, mathematically, I would take my 30 degrees, and we're going to add, from here I'm going to go my 30 degrees, so I go 30 degrees, and I'm going to go another revolution to there. So wouldn't I add 360 degrees to that? Visually and mathematically, that makes sense. What angle does that give me? What is 30 and 360 degrees equal? 390 degrees. So that is a coterminal angle to 30 degrees that is positive. So not to mess up our graph overly much, we're going to draw another graph for a negative one. So here's our negative graph. We still have our 30-degree angle here. But this time we're going to go in a negative direction. So I want to go, but I start, notice that I start still at the initial side. So if I'm going to go in a negative direction, I'm going to go from here to here only. I don't make a full 360 degrees, so my negative angle is going to be less than 360. But I still start with my 30 degrees. Then instead of adding 360, mathematically I'm going to subtract 360 degrees. What does that give me? Negative 330 degrees. So we always add full revolutions and always subtract full revolutions. If adding or subtracting a full revolution does not get you your positive or your negative answer, you might have to add or subtract another full revolution. So we just keep adding and subtracting full revolutions until we get the positive answer we're looking for or the negative answer that we're looking for. And I'll show you what I mean as I get to a bigger number here in a minute. So are we okay with that? No questions on that? Makes sense? All right, so look at the negative one. So this time you start with a negative value. Let's draw where that is. What quadrant is negative 150 degrees going to be in? I'm going to start here and go negatively. So negatively, this is 0 degrees. Isn't this negative 90? And isn't this negative 180? So isn't it in between these two? Right? So I'm going to draw my terminal side here. And technically, my angle, my negative 150 degree angle is there. So I want a positive angle that co-terminates there. So if I start at my initial side and go in a positive direction, won't I just be going to there? Won't that be an angle that's less than 360 degrees? In fact, it'll be somewhere between 180 and that'll be 270. So it should be somewhere between 180 and 270. So let's see mathematically what that gives us. I'm going to take my angle of negative 150. And what do I do? Add 300, a full revolution, 360 degrees. What does that give me? (210 degrees. Didn't we say that we would get a degree measure between 180 and 270? And isn't that between 180 and 270? So that's going to equal that 210 degrees. So it makes sense. Then we're going to look at our negative value. So let's draw another coordinate grid. We're going to put our terminating side here. And this is our negative 150 degrees. So this time I want to go negative. So I'm going to travel that negative 150 degrees, but I need to terminate here again, so I have to go all the way around and hit it again. So it looks like a little snail track. So mathematically, I still take the negative 150, but what do I do with my 360 this time? Subtract it. So because I'm making more than a full revolution, I should get more than 360 degrees. So they're both negative. What do you end up with? Negative 510 degrees. And that is more than 360, and that makes sense. Because I went one full revolution, there's negative 360 plus another negative 150. Well, I started with negative 150. That's what I started with. And so I had to go in a negative direction. So that puts me in that third quadrant. Does that make sense? Okay. And I'm always adding in both of these. I always added or subtracted. So I added to get my positive, subtracted to get my negative. Now, it's possible I might have to, like here, what if I start out at 510 degrees? Let's just start with that. What if I gave you 510 degrees? In order to get a positive angle, wouldn't you add 360? If you add 360, won't you get negative 150? Is that a positive angle? No. So wouldn't you have to add 360 again? So sometimes, my point is, sometimes if I give you a big enough positive angle or a big enough negative angle, you might have to add or subtract more than one full revolution to get to your positive and negative answer that you're looking for. So do bear that in mind. These examples that I've given you, we're only adding and subtracting one revolution, but you can add and subtract numerous revolutions. This is not the only answer to my question. You could have subtracted 360 again and again and again and again, and that would be an acceptable answer. I would highly suggest you don't. You don't want to irritate your math teacher. She's grading your paper. Just saying. You want me happy when I'm grading your paper. So let's stick with one or two revolutions. All right, so let's move on to gradient measure. Gradient measure just means you have to have a shift in your brain as far as how you're thinking about the unit circle. We're no longer thinking in degrees, we're thinking gradients. So as I draw my picture up here, bear in mind that this is 0 radians. This is pi over 2 radians. This is pi, 3 pi over 2. Now I really only pay attention to 0 and pi, because depending upon what my denominator is here, in this case it's a 3, it will depend on how I partition the top half of the coordinate grid versus the bottom half of the coordinate grid. If this is partitioned into a divisor of 3, I'm going to divide the top half into portions of 3, because this is 1 whole pi. So if this is 1 whole pi, wouldn't you agree that if I partitioned it in thirds, this would be pi over 3, 1 pi over 3, this would be 2 pi over 3, and then this would be 3 pi over 3. 1, 2, 3 pieces. Are we all in agreement as to how I did that? 1, 2, 3 pieces. Yes. Isn't 2/3 of a pi, so 1/3 of a pi is less than a half of a pi, right? But wouldn't 2/3 of a pi be more than a half of a pi? So my second third has to be in between these two. And then my third of a pi is here. So if you ignore that 1/2, you have 1/3, 2/3, 3/3. The same thing occurs over here. 1/3, 2/3, 3/3. So for this particular circle, I'm going to count by third of pi's. So let's put in our terminal side. This is 0. So if I want to have a terminal side of 2 pi over 3, here's 1 pi over 3. And here's 2 pi over 3. So my terminal side is going to be in quadrant 2. So from here to here is 2 pi over 3. I traveled 2 pi's over 3. If this were divided by 12, I'd partition this into 12 pieces up here, and this into 12 pieces down here. Whatever this denominator is, that's what you partition each half into, that number of pieces. And that's the only way you're going to be able to count. Fortunately, we don't have to always count. We can do it mathematically. Okay. So let's find our positive angle. So if we're doing our positive angle, we still start always from the initial side, same as always. I'm going to go from here to here, but that's still 2 pi over 3. So I have to go an additional revolution and get down to here. So mathematically, I'm going to take my 2 pi over 3, same as we took our degree angles, and I'm going to add what to it? A full revolution, but in radians, would that be 2 pi? But 2 pi is not a fraction, so I turned it into a fraction. What's the denominator that I want to have? A denominator of 3. So I want to multiply this by 3, so I multiply the numerator by 3. What's this numerator now? This is 6 pi, plus 2 pi gives us what? So this equals 8 pi over 3. We're going to test that by counting. That's going to prove to you that it works. So if I count my green path, so watch my green path, I'm going 1, 2, I'm looking at my tick marks out here that I made, 3, 4, 5, 6, 7, 8. So I ignore my axes, I'm only looking at the green tick marks. Then I get 8 pi's out of 3. I ignored these axes here. These I kept because they're part of my tick marks. So again, 1, 2, 3, 4, 5, 6, 7, 8 pi over 3. So you could, and you're going to start to get used to counting in terms of pi, you could just count your pi's and you to get there. The problem is if you have really big numbers. So that's our answer there. So the good thing is you can always do it mathematically. Let's look at the negative one. So let's draw this again. Our terminal side is over here. From here to here is 2 pi over 3. And again, I'm going to partition this into, here's 1. Well, that's not really 1, that's 0. This is 1. This is 2, 3, 4, 5, 6 again. So I've got 3 pi here, 3 pi there. I want to go negative. So I can start here and go in this direction. Boom, I hit it. Less than 2 pi. So my answer should be less than 2 pi. And let's just count it and see what we should end up with. If I start here and I count, don't I have 1, 2, 3, 4 pi? But then I go in a negative direction. So what's it going to end up being? Negative 4 pi. So let's see if it works mathematically. I start with 2 pi over 3. But what do I do? What am I going to add or subtract? I'm going negatively, so do I add or subtract? I subtract. I'm subtracting a full revolution in terms of radians, so isn't that 2 pi? But I can't use 2 pi the way it is. I have to have a like denominator, which is 3. So I multiply this by 3 and that by 3. So, isn't this negative 6 pi here? What's a negative 6 pi and a positive 2 pi? I get a negative 4 pi over 3. Isn't that what we thought we would get? So mathematically it worked out as well. But you have to be able to draw it and do it mathematically. They complement each other. Questions on that before we look at a bigger one? Alright, so this time it's negative 7 pi over 6. So our denominator is different. What are we going to partition the top half into? 6. So I'm going to draw my coordinate grid. And I want to partition the top half into 6. So this is where 0 is, and this is where pi is. So this is 1, 2, 3. So this axis is actually one of our tick marks now. And this is 1, 2, 3. So I have 1, 2, 3, 4, 5, 6 pieces. I'm going to do the same thing here. So this would be 1, 2, 3, 1, 2, 3. One purpose of that is so I can count. So this starts out at negative 7 pi over 6. We have to go in the negative direction. So we're going to count negative 7 pi's because I have it partitioned to 6. So here's negative 1, 2, 3, 4, 5, 6. Isn't that negative 7 pi over 6? So I end up in quadrant 2 from here to here is my negative 7 pi over 6. Now, if I want to go positively, I again start here from the initial side. Don't I just have to go from here to here? That'll get me positive, won't it? I'm going in a positive direction. I hit that terminal side. Done. Count. 1, 2, 3, 4, 5. Shouldn't it be 5 pi over 6? Let's see if we get that mathematically. So, we're going to take our original negative 7 pi over 6, and what am I going to do? Add or subtract? I'm going positively. So I'm going to add 2 pi over 1. What do I want to convert the denominators into? 6. So times 6 times 6. So what does this give me here? This right here. You're not watching. 12 pi plus a negative 7 pi is what? 12 and negative 7? 5 pi over 6. And isn't that where we said we would end up at? Which we did. So let's go negatively. Doing the same thing. Here we go. We know already we're ending up in quadrant 2, right here. This is our from here to here. are negative 7 pi over 6. Let's partition it out. Ellie, you with me? You don't know. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 6 and 6. So this time we're going negatively. So I want to still start at the terminal side, but I'm going to go in the negative direction. Well, if I go from here to here, isn't that still negative 7 pi over 6? Right? So I have to go a full another revolution right there. So mathematically, we're going to start with negative 7 pi over 6 and do what? Add or subtract. We're going negatively. So we subtract 2 pi over 1. Denominator is 6, so I want this to be 6. So times 6 times 6. What's this right here? Negative 12, negative 12. What's negative 12 and negative 7? Negative 19. So we should get negative 19 pi over 6. So I'm going to count to make sure that I hit negative 19 tick marks. So from here, I hit 1, 2, 3, 4, 5, 6, 7. There's the first one. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Did it work? It worked. Any questions about drawing or finding those mathematically? Just a matter of getting used to it. Are we okay with that? Yes. Whatever denominator you start with, because your 2 pi is always going to be over 1. Just multiply top and bottom by whatever that denominator is. So it shouldn't be more complicated than that. And then if, for some reason, like for instance, let's say I started out with negative 19 pi over 6, and you added 2 pi to that, which is really what, 12 pi over 6? If I add negative 19 and add 12 pi over 6, doesn't that give me negative 7 pi over 6? Well, I didn't get my positive answer, so wouldn't you have to add another 12 pi over 6 to get to a positive answer? So sometimes, again, if you have a big enough starting angle, you have to add 2 revolutions or even sometimes 3, right, Logan? Right? Yeah. Uh-huh. Okay. So then example 2 looks at it in a different way. This time we're finding the 6 trig functions whose terminal side contains a given points. So what does that mean? Let's draw a picture. And we're going to plot that point 5, 3. I can't believe you don't find this fascinating. So this is the order pair 5, 3. So this is the path from the origin to that point that is created. Doesn't that create an angle? And this is our initial side here. Immediately, you will 100% of the time when you're trying to find the 6 trig functions, well, I have to have an angle to find those in a triangle, no less, a right triangle. So I need to create a right triangle with this as my hypotenuse. 100% of the time, the right triangle will go towards the x-axis. Never, 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 never go to the y-axis. Did I put enough nevers in there? No. It will always look, you're just always going to go to the x-axis. Always. Don't ever make a right triangle to the y-axis. One? Because I said so. Just one or 3 times you'll hear me say that. You'll see why we're going to use a reference angle. And I don't want to use the y-axis for my reference angle. That's just not good. Okay, so 100% of the time you'll draw for these particular problems a right triangle to that x-axis. And so we get this theta in here. In our case, we went from the initial side to the terminating side that is blue, and our theta is what I call a reference angle. The reference angle and our theta are one and the same thing. I'll show you when they're not. Do I really know the length of this side here? What's the length of this side? 5. And what's the length of this side here? 3. can't I find the length of the hypotenuse, which we'll call x? Yeah, then this is not a triple because this can't be 4, right? 4 is not bigger than 5. And so we're going to take 3 squared plus 5 squared equals x squared. 9 plus 25 is equal to x squared. What's 9 plus 25? 34 equals x squared. So what is x equal? Square root of 34. So this is square root of 34. Now that I know all 3 sides of the triangle, can I find sine, cosine, and tangent? So that's what we're going to do. Yippee skippy. We're going to find sine of theta. We don't know what theta is, but it doesn't matter. We can still find sine. So sine is opposite, in this case 3, over the hypotenuse of radical 34. I'm personally okay with that as an answer because your textbook is going to now start to waffle between rationalizing the denominator and not rationalizing the denominator. I did notice that the answers in Math Excel look like this.
Yeah, I noticed that too.
Now you can try 3 over radical 34 and see if they'll accept it. If they don't, did they not?
No.
Because they did yesterday.
They accept it some.
Well, they won't accept it this way if the 3 and the 34 can reduce, and that's what some of you ran into. So if this had been, I don't know, 39, and you went 3 radical 34 over 39, they won't accept that. You have to reduce any numbers outside the radical. So that could have been what you guys were experiencing yesterday. Is that? You also have to simplify what's underneath the radical. So if there's a perfect square underneath the radical, that's another thing that you guys are experiencing that you were having issues with. If there's a perfect square under there, you need to find it. Well, 34 is 2 times 17, isn't it? There's no perfect squares under there. So we're good on all accounts. I have a feeling they'll accept both answers, and if I were you, I'd stick with that answer. Isn't it easier? Are you okay if I go from here to here and not show the rationalizing?
Yeah.
Are you? Because all I did was rad 34 over rad 34, and so those we can't do anything other than multiply together, and that becomes just 34. So if you have an issue, you can show that rationalization. And so then cosine of theta is adjacent, which is 5, over the square root of 34. And again, rationalize, that would be 5 radical 34 over 34. And then tangent, we're going to squeeze it in here, is equal to opposite, which is 3, over adjacent, which is 5, so it's 3 over 5. Never, ever, never, ever, never, ever slash your fractions. It's a terrible, 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 terrible habit to get into. Did I put enough terribles in there? Girls, you are the worst offenders of the slashing of the fractions. Stop it. I know it saves time. No, but it just is true. It's not sexist, it's a fact. So whipping the slasher. No, it's hard to tell what the denominator actually is. Because if I had something like 5 plus the square root of 2 over 3, and you wrote it as 5 plus the square root of 2 slash 3. It looks like 3 is only the denominator of that. Right? As we get more complicated fractions in this class, which we will, you've got to put slash in those fractions. Just stop it right now. Yeah, so don't slash them. Okay, so then for my, what is the inverse of sine? Cosecant. So cosecant of theta, again, I'm going to use the unrationalized one. Much easier. Square root of 34 over 3. And then secant of theta, don't forget the theta part, square root of 34 over 5. So once you get the size to your triangle, it's no different than what we were doing today. And then cotangent of theta is equal to 5/3. That's okay. So are we okay with that? Now, it is also important to pay attention to signs. All of this was positive, and our terminal angle and our theta, our reference angle, was all one and the same. We'll look at B. B's a little different story. So we're going to draw our picture here. And we're going to put in -4, -3. So that would be right about here in quadrant 3. And the pathway from the origin that's created looks like this. So technically, my angle goes from here to here. This is theta. Wouldn't you agree? However, I can't make a right triangle out of that. I can't make a right triangle with an obtuse angle, can I? No, and it's really more than obtuse. It's more than 180 degrees. But instead, I can immediately create a right triangle to the x-axis, not the y, always to the x-axis, this way, can't I? And this is my new reference angle here. So I'm just going to call it theta. Technically, they're not the same. But my reference angle and my angle here, don't they both have the same terminal side? Angles that are coterminal all have the same sine, cosine, and tangent and inverses. And so we use that knowledge and use a smaller angle that creates this right triangle in order to find those values. I now know the sides of this right triangle. What's this distance? It is negative. Make sure you have the proper signs in there because it'll affect. Sine, cosine, and tangent can be either positive or negative. It depends on what quadrant your angle is in. And so this here is -3. And then what is our hypotenuse? 5. 100% of the time, the hypotenuse of this right triangle is always going to be positive. Your hypotenuse cannot be negative. Ever, ever, ever. I have a lot of words I'm repeating today. And so, now we can find sine, cosine, and tangent. Remember, this was a triple, that's why we didn't use our Pythagoras theorem. So here we go. Sine of theta. Now you have to be careful about your degree of reference because my triangle's a little upside down. So if that bothers you, you have to redraw it with the proper sides and sines attached to it. But if this is my angle of reference, opposite is -3, hypotenuse is 5. So I've got -3 over 5. Cosine, adjacent is -4 over +5, so my cosine is negative. But look at my tangent. My tangent is opposite is -3. Adjacent is -4. You best not leave your answer like that ever, because what does it simplify to? 3/4. And if you try to put that into Math Excel, they will mark it wrong because your two negatives will cancel. And then your inverses fall easily into place from here. So cosecant of theta is -5/3. Secant of theta is equal to -5/4. And cotangent of theta is equal to +4/3. So questions, problems, or concerns? Now they could also, those are just with ordered pairs. So the ordered pairs are not going to give you gradient measure. Seth? So the reference angle is the one inside the triangle, and that's different than the actual theta itself. But the reference angle here, which you could call some other Greek letter if you want to choke onto it, these both have the same terminating side. All angles that have the same terminating side, no matter what the degree measure is, will all have the same sine, cosine, and tangent. And so if we just use a reference angle rather than whatever that big angle is, which I don't know what it is right now, then I'll get the same measures here. So one of the theorems that we're going to use is that all coterminal angles have the same trig function values. Okay, any other questions, concerns, comments? Okay. So then let's look at something slightly different. Instead of giving you an ordered pair, what if I actually gave you the degree measure itself? So instead of plotting an ordered pair, you're going to plot a terminal side in the quadrants that that belongs. So all I care about is that you recognize where 315 degrees is in the coordinate grid. Is it in quadrant 1, 2, or 3? Well, this is 0 degrees, 90 degrees, 180 degrees, and 270 degrees. So doesn't it belong, and then this is again 360. So doesn't it belong between these two? I don't care where you draw it, as long as you draw it in that quadrant. I'm not going to be picky and say, oh, I'm sorry, you drew a 320-degree angle. It's wrong. I would never do that because the purpose is just to figure out what quadrant it's in so we can figure out the signs that we're dealing with. And so there's my angle. Technically, my angle goes from here to here. So this is my 315-degree angle. So this time I know my angle. I don't know my side measures. But we're going to do the same thing that we did with the ordered pair. Immediately, I'm going to make a right triangle to the x-axis. Always the x-axis. I don't know what theta is inside here, but I can certainly find out what it is. Why? Always look, since I'm always making my right triangle to the x-axis, always look at 360 degrees or 180 degrees. Isn't this angle closest to 360 and not 180?
Yes.
So I'm going to take to find theta, whichever one is bigger, 360 or my angle measure, in this case 315, it's going to come first. My reference angle will always be positive. It will not be a negative answer. Even if your reference angle is negative, even if this angle here is negative, our reference angle will always be positive. So I'm going to take 360 degrees because it's bigger than 315, and I'm going to subtract from that the 315 degrees. What do I get? So theta is equal to 45 degrees. Isn't that a special angle?
Yeah.
If this is a 45-degree angle, isn't this a 45-degree angle there? And don't you know the side lengths of your 45, 45, 90 triangles? We are going to hypothetically create a radius of that central angle as being 1. And that's why our special right triangles always have at least one side that's 1. And so, isn't this a positive 1 distance here? What's this? It's a negative 1 distance because this direction on the y-axis is negative. So you have to pay attention to your signs in your special right triangle. The hypotenuse is rad 2. Again, your hypotenuse one. I swear I turned that off. See, I don't have. Why would my daughter call me in the middle of the day? I don't
That
have.
could be an emergency. I think
It's not. She would call. You know what that thing is? A landline phone. She'd actually call the landline phone. She knows I won't answer. She knows I won't answer.
it's not all the cities right here.
Anyway, I don't have a case on this phone, and now that I don't have a case, this is like turning on and off all the time. My butt is turning it on and off all the time. I need to get a case ASAP.
ASAP.
Excuses. It's
ASAP
off
rock.
now. Fun. All right. So back now, I was so rudely interrupted by my daughter. Thank you, Stephanie. All right. Stop. We're not going to talk about that right now. All right. So I've got my special right triangle. Always, you've got to fill it out. Now, from there, I can find my sine, cosine, and tangent. I will tell you, and we're going to say a sine of 315 degrees, because isn't that the angle that I'm trying to find?
Yes.
Because 315 degrees and 45 degrees, really in this case it's a negative 45 degrees, but we ignore the fact that it's negative. They're both coterminal. They both have the same terminating side, so they should all have the same trig function values. So, but pay attention to your signs. Opposite, this is my reference angle right here. Opposite that is a negative 1 over the hypotenuse of rad 2. I will not accept for your special right triangles, that is the sign. And you'll see why tomorrow when we go over the unit circle. You've got to rationalize that. Rationalize, isn't that negative radical 2 over 2? If I multiply top and bottom by rad 2 over rad 2, then I get that. So then your cosine of 315 degrees.
So that's the answer you're going to accept.
This is the answer that I want for all your special right triangles. They all have to be rationalized. I don't want, and you'll see why later. We need to look at it in the rationalized form. For your cosine, isn't the adjacent a positive 1? Your cosine is actually a positive 1 over rad 2, which rationalizes as positive rad 2 over 2. So know your signs. Your tangent of 315 degrees Opposite is -1. Adjacent is +1. So overall, we have a value for tangent of -1. Notice that only one of the functions was positive. In all quadrants but one quadrant, all the functions will be negative but one. There's only one quadrant where they'll all be positive, and I'll talk about that in a minute. Allie, are you still with me? Okay. Are you writing? So then cosecant of 315 degrees, I would be taking the inverse of this one, negative radical 2. Secant of 350 degrees, inverse of this is positive radical 2. And then cotangent of 350 degrees, the inverse of this, the reciprocal, is still -1. I don't take the opposite sign, I just take the reciprocal, so the sign always stays the same with reciprocals. So the signs of the inverses should be identical. All right, so then I want you to do 210 on your own. So find out where 210 goes in the coordinate grid, so draw it. One. Yes, because that's really what I'm asking you to find are these ones. We're just using a reference angle of 45 degrees to find those, but we're really finding the sign of 315 and so forth. So we do have to have the 315 in here and not the 45. We're only using the 45. Oh, do you have to have it in there, period? Yeah. Yes, you can't just do sine equals. Because a lot of you do get in the habit of leaving out your theta or your sine measure or your degree measure, and you can't get in that habit because it's always sine of what? Tangent of what? And if I don't know what it is, it'd be an x or a theta. Because pretty soon we're going to find out what that measure is using, well, we did the other day, using our inverse trig function. Well, we haven't done that yet, have we? Actually, we haven't. All right, so find all the six trig functions of 210. Yes. No, it's positive 210. Your reference angles are always positive. It doesn't matter about the reference angle. Oh, I see. It's a level 0. Oh, we don't have my perspective. So yeah, we have a level 0. Oh, wait. Correct. So 210 is in what quadrant? Third quadrant. So you're going to draw it in quadrant 2, right? And then immediately you're going to draw a right triangle to the x-axis. And so from here to here is your 210 degrees, but this is your theta from here. And since that's 210 and it's closest to 180 degrees, that's what I'm using to get my reference angle. And so 210 is bigger. So to get my reference angle, I'm going to take that 210 degrees and I'm going to subtract my 180. And so theta turns out to be 30 degrees. So I know that that's a 30-degree angle. And so from there you guys can list your special right triangles for 30, 60, 90. Always across from 30 degrees is what number? 1. And in this case, is it a positive 1 or a negative 1? It's negative, because that direction below the x-axis for y is negative. And then across from the 60 is always what? Rad 3. So is this a positive rad 3 or a negative rad 3? Negative. This is negative. And then your hypotenuse is 2, and it's always positive, no matter what quadrant. So now find your sine, cosine, tangents of 210 degrees. And 30 degrees is your reference angle, not the 60. Don't forget to rationalize. Are you ready? Maybe. All right, so there are your values. Note that for secant and tangent, you had to rationalize. Those are special right triangles. I expect those to be rationalized. The other ones I don't mind, so long as you simplify what's underneath the radical and you simplify anything that's outside of the radicals, fraction-wise. So any issues, problems, or concerns with that? You good and comfortable with that? All right, so let me just share something. I'm going to zoom out of this a little bit. Let's just observe something about these 4 problems. Notice that I've got 4 problems in all 4 different quadrants. In quadrant 1, notice that all sine, cosine, and tangent were what sign? Positive. This one, oh, I don't have one in quadrant 2. Well, we'll talk about that in a minute. In quadrant 3, which these 2 were both in quadrant 3, what do you notice about sine, cosine, and tangent? Which one was positive in both of these? Tangent. And of course their inverses are as well. Then in quadrant 4, which one of these was positive? Cosine. So in all quadrants but one, there's always only one trig function out of sine, cosine, and tangent that is positive. Quadrant 1, they're always positive. So that's the one quadrant where they're always positive. In quadrant 2, 3, and 4, only one of them is positive. Well, here's how you can always tell and check. So flip this to the unit circle, and the only thing that I'm going to talk about regarding the unit circle today is your signs. And this should ring a bell. You should have seen this last year, my hope is. This is quadrant 1, 2, 3, and 4. So that goes counterclockwise in the positive angled direction. This A represents all. This S represents the word students. This T represents the word take. And C represents the word calculus. All students take calculus. It goes starting in quadrant 1 and goes counterclockwise. All students take calculus. And this is the way I remember it. And that means that all functions are positive here. Only S for sine, only sine is positive in quadrant 2. That means that cosine and tangent should turn out to be negative. Only tangent is positive in quadrant 3, so sine and cosine should turn out to be negative. And only C, cosine, is positive in quadrant 4, so sine and tangent should turn out to be negative. So as I'm doing problems like this on this other side, as I finish my problems, I'm going to look at my answers and go, okay, quadrant 1, all should be positive, yes, all should not be positive. Quadrant 4, all students take calculus, cosine. Only cosine is the one that should be positive, and sure enough, everything else is negative. So you can kind of check your signs that way, because it'd be a shame to get half credit because your signs are off. So that's one thing that you're going to use to check that. And of course, in Math Excel, you'll have the answer right, but the wrong sign, and they'll say it's wrong. You're like, I don't know why it's wrong. Well, you have the wrong sign. Fine. That thing's blowing overhead, so sorry. So if I got a -1, if this were in quadrant 1 and I got a -1, it would be incorrect. Now, if you're checking it on your calculator does not know what quadrant your reference angle is in. So if you try to, now I will say that there's a difference between putting in 315 degrees in your calculator versus 45 degrees. If I put 315 degrees in my calculator knows that that's in quadrant 4. But if I put 45 degrees in my calculator, it thinks it's in quadrant 1. So it will 100% of the time give you a positive answer for sine, cosine, and tangent. But if I put 315 in my calculator, it knows what quadrant it's in, and it will give me the proper sign. But it's not going to give me the exact answer. So it should kind of clue you in that you've done something wrong, or maybe attached the wrong sign within your special right triangle. All right, so again, I emphasize, hold on to your seats, to not start section 4-3 homework tonight, because there are certain problems I have not lectured on. Number one, I haven't talked at length on the unit circle, nor have I discussed these particular problems here, which you're going to run into some of these problems that I have talked about, but they're just different situations that you're going to want to know what to do with. And so rather than frustrate yourself, please don't start your homework until tomorrow night. So if you have not completed section 4.1 or 4.2, for shame on you, number one. But number two, get it done tonight so that the 19 problems I've assigned that you have over a week to finish because of the 4.5-day weekend, there should be no reason why we don't have it finished. In addition,